Hello, good morning, good afternoon, or good evening, whatever time you're watching. Again, this continuation of our Coulomb's Law video, and I will just have two problems, I guess, very basic, and then I will upload another problems that, with difficulty already, and it's related to still this law. All right, so let's recall the basics about Coulomb's Law. The like charges will repel positive and positive, and then negative, negative, they will repel. The arrows say so. Okay, they are pointing away from each other. Meanwhile, positive and negative, they are unlike signs. The arrows are pointing towards each other, showing that there is an attractive force behind. And the force that I said in my previous video, the force that interacts between these two charges is called Coulomb's force or electric force or electrostatic force. Okay, so we have the needed variables in studying or calculating the Coulomb's force. We need to have the distance, and it must be in meter. Distance or R. Okay, remember that Coulomb's force is inversely proportional to the squared of the distance of these two charges. Okay, so distance or R, it must be in meter. If in the problem the distance is in centimeter, so you have to convert it to meter before you will do the calculation to jive with the units of our equation. Okay, and we also have the value of charges, very needed because when you multiply charges, it will determine the amount of Coulomb's force. It's directly proportional. Okay, so again, we need the distance in between these two charges, unlike or like charges, and we also need the value of our charges. So in this case, as you can see, we have positive charge here, and the value is 3 times 10 raised to 6 coulombs. And negative charge here, the value is negative 2 times 10 raised to negative 6 coulombs. As you can see, there's a negative sign here to represent it's the electron or the negative charge. Positive, obviously, it's for proton or positive charge. But it doesn't make sense because our equation will have the absolute value of these two charges when we multiply these charges together. All right. So let's begin. We have this illustration here, and the question is what is the magnitude or the value and direction of the force between two charges? Okay, shall I say it's the direction of the forces? We have two charges here. We have positive, and the value of the charge is 3 times 10 raised to 6 coulombs. And negative, since it's a negative charge, so we have negative 2 times 10 raised to negative 6 coulombs. Let's try to find out the magnitude and the direction of this charges. I mean, the direction of the forces in between these charges. We have a distance between these two charges. It's 3 meter. It's already in meters, so no need to worry. You can calculate it directly. Okay. And then that's charge one. Let's say it's charge one. Positive is the charge one. Charge two is negative. And this is the formula or the equation for Coulomb's law. We have force or the Coulomb's force is equivalent to the constant. Coulomb's constant, charge 1, charge 2, multiply, get the absolute value, and then over r squared or the distance. We have the value of r, it's 3 meters. We have the value of charge 1, it's very clear, and charge 2. But yeah, what's k in here? Okay. K depends on, or Coulomb's constant, or K, depends on the situation where these charges are isolated or located. So let's try to find out in the problem where these charges are being situated. Is it in a vacuum, in plastics, in glass, or in air? Let's try to find out. So going back, um, what is the magnitude or the value of the forces between two charges? We have charge 1 and charge 2. We have the values of each charge, and then it's in the vacuum. So the Coulomb's constant in a vacuum, it is equivalent to these numbers. It's 8.99 times 10 raised to 9 um, Newton meter squared per Coulomb squared. That's the unit of our Coulomb's constant. And and this will be the value of our K every time that the charges are in vacuum. So please remember. So we will have force on 1, please recall, force on 1 due to 2. So let's say force 1, it's the first charge written, so it's going to be the one that will feel the force or the influence of charge 2. So charge 1 is our focus here. So charge 2, what will charge 2 do to charge 1? Charge 2 is negative, and then charge 1 is positive. So therefore, charge 2 will have to pull charge 1 towards it. So the direction will be definitely right. Okay, it's going to the right. Now we will have the Coulomb's equation here. So we have charge 1 and charge 2 in K since it's in vacuum, so we put it there, the value of K. And then we also perfectly put it there, the values of charge 1 and charge 2. If you look at the illustration again, charge 1 is 3 times 10 raised to negative 6, so we put it here. And the other charge here, negative. But don't worry about the negative sign here because we will just get the absolute value of the product of charges. And we will divide it by the r squared. So r is 3, so we put it there, r squared. And we will do the math. Of course, we will multiply all the numerators together. We have imaginary 1 here. So numerator 8.99 times 10 raised to 9, and then multiplied by the absolute value of the charges. And then you will have this product here. It's, hold on, it's 0.05394. That's the product of all the values in the numerator. And then you will divide it by the square root of 3. 3 times 3 equals 9. So the quotient will be 5 times 10 raised to negative 3 newtons, the unit of force, and it will be to the right. So Q2 will have to pull positive towards it. So direction will be to the right. Now, if we will change the orientation, charge 2 will gonna be our point charge or our let's say the focus, simply the focus. So we have force on charge 2 due to charge 1. Charge 2 will have to feel the force, and then charge 1 will do something to charge 2. Since positive and negative will attract, so charge 2 will be pulled towards charge 1. So definitely the direction will be to the left or negative. So we will put again the same magnitudes. Okay, the same magnitudes, just that the direction will differ. It's like the third law of Newton. It's the interaction. So the same thing will happen, the same magnitudes, and then you will have the same result. But then again, the direction is different. It's now to the left. Okay, if you notice here. And this time, another problem, an astronaut is on a spacewalk and accidentally drops two small metallic spheres into space. One sphere carries a charge of positive 2 times 10 raised to negative 6 coulomb, so it's going to be positive charge. And another positive charge. The other small metallic sphere is 5 times 10 raised to 6 coulomb. So this is another positive charge. A tiny device measures that the interaction or the repulsion, it repels because obviously positive and positive. The force of repulsion will be 0.20 Newton. The question is, how far? So we will be finding or figuring the distance in between these two positive charges. How far apart are the two spheres floating in space? And it's in space, so we will still use the Coulomb's constant in vacuum, the value that I introduced earlier. So we have two positives, and then charge one, and then charge two. We have the values of the charges, and we also have the repulsion force. Remember, it's going to the right. That's force two due to one, right? Force two is not force two, charge two is our reference point or the point charge, and what will charge one do to charge two? So it will gonna push charge two. So you have this direction. Same is true with this one, going to the left or negative. Okay. Repulsion is given in the problem. It's 0.20 newtons, but we do not know the distance in between, so it's unknown. How to do it? So we will still be using the formula, but by the way, it's in space, the vacuum, so still we will be using this figure as the Coulomb's constant, or K. We will use the equation in coulombs, and we will substitute the available values there in our problem. We have, but we will try to rearrange first the formula in order to isolate R, because that's the unknown that we need to know. Okay, so of course we have a imaginary one here so that we can do the cross multiplication. We will multiply R squared in F and then one with uh, this variables here in the numerator. So F multiplied by R, so you will have FR here, and then 1 times K and the absolute value of charges. So you have it there. To isolate R, all you need to do is to divide both equations by, of course, force. And then we can cancel force here and force here. So we can have R squared is equal to constant charges, product of the charges over force. And then since we need to get rid of squared here, so we will square both equations. So we can get the radical sign here. So our formula to get the radius or the distance will be square root of k, product of charges over force. So let's substitute now the values. We have it there. The k is, since it's in a vacuum, so you will be using 8.99 times 10 raised to 9. That's it. And charge 1 in our illustration is 2 times 10 raised to 6. That's positive. We put it here. And then another charge, another positive charge, 5.10 raised to negative 6 coulombs. So we put it here. We will still get the absolute value. And then our force, according to the problem, it's 0.20. So we will put it here. And we will do the math. We will multiply all the things in the numerator. We can come up with 0.0899. That's the product of this values here, or magnitudes here, divided by F, 0.20. So the quotient will be 0.4495, and we will get the square root of it, and then we will have 0.67. The unit will be in meter because we were dealing with the radius. I hope it makes sense, and I hope this problem helps you in solving basic problems about coulombs. So I will be uploading another practice problem related to Coulomb's law with a little difficulty. And yeah, I hope you like the video. If it helps you, you can share, you can like, and then you can subscribe. Yeah, that is how you will show your support in what I do. Thank you so much, and see you around till next time. Bye for now.